LoRA adapters are to me one of the smartest strategies used in machine learning in recent years. LoRA came as a very natural strategy for fine-tuning models. In my opinion, if you want to work with large language models, knowing how to fine-tune models is one of the most important skills to have these days as a machine learning engineer. So let me show you the mathematical foundation for those LoRA adapters, why they are useful, and how they are used. Let's get into it. So I want to address a technique that is often used to speed up the fine-tuning process and to reduce the memory requirements to fine-tune such a big model. This is called LoRA, which means low rank adaptation. So let's dig into the details of why this strategy works. So before we can understand this technique, we need to understand what fine-tuning means when it comes to the backpropagation algorithm. Here is the basics of the gradient descent update. So we take the original value of the model parameters and we update them by computing the gradients of the loss function. And we get the new value of the model parameters. These capture one iteration of the gradient descent update, and this happens at every iteration of the backpropagation algorithm. So a trained model, when we look at a set of parameters, so for example, we look at a linear layer, a trained model is just a sum of different gradient updates. So here is the original value of the model parameters, the values that they had when we initialize them, and then little by little we update those values. At the first iteration of the backpropagation algorithm, we compute the loss function, we compute its gradient, and we subtract its value, and we do the same thing at each iteration of the backpropagation algorithm. So let's try to understand what is a fine-tuned model. To have a fine-tuned model, we start from a pre-trained model. A pre-trained model is a model that has been trained on some dataset. So when we consider a set of parameters, we just take the initial value of those parameters and we subtract this sum of gradient updates. Here I'm simplifying by looking at the basic gradient descent algorithm, but obviously you can do the same thing with other optimizers, like Adam, for example. So when we fine-tune a model, what we do is we add some more data. By using that data, we're going to train further the model. Training further the model means that we're going to compute additional gradient updates, and we're going to add them to the previously computed gradient updates. So when we look at the model parameters of a specific model, we can decompose those model parameters into a sum. We have the initial values of these model parameters at the moment that the model was initialized. We have the sum that relates to the gradient updates that when we pre-train the model, and we have the sum of the gradient updates when we fine-tune the model. So here we go from t equals 0 to t minus 1. Capital T is supposed to represent the last iteration of the pre-training, and capital F is supposed to represent the number of iterations that we did when we fine-tune the model. So we have this decomposition, where the model parameters can be decomposed into the values that relates to training the model and the values that relates to fine-tuning the model. So here I have theta t, which is equal to this sum that relates to pre-training the model. And here I have delta w that captures this sum that relates to fine-tuning the model. By summing the two, I obtain what I call theta f, which are the model parameters once the model is fine-tuned. So if we consider the transformer model, can we modify the architecture such that we are mimicking this decomposition of terms? So let's consider, for example, the original attention layer and the original feed-forward network. So I could mimic the term that relates to fine-tuning the model by just adding a set of parameters to the model. So here I take the original attention layer, I take another matrix, and I just add it next to the original attention layer, and I add the result of the two matrices. Obviously, the attention layer is not purely just a matrix, but I'm simplifying here for the sake of explanation. So by adding these two matrices, I can recover this kind of decomposition of terms. So you can imagine that the matrix here relates to the pre-trained model, and this matrix here could relate to the learning that we do when we fine-tune the model. And we can obviously do the same thing for the feed-forward network. So we could add to each of the matrices new matrices that would capture the concept of fine-tuning. So instead of accumulating the gradients in the original layers, we are creating a new matrix to accumulate the gradients there. So we don't need to touch the original layer to actually continue to fine-tune the model. We could add new matrices that are going to capture the learning that we do when we fine-tune a model. And because we are able to decompose pre-training and fine-tuning into a sum, we can easily sum the results of the matrices. For this to work, we need to make sure that delta W has the same dimensions than theta T. So right now, there's not a lot of advantages to have separate matrices to capture the learning that we do during fine-tuning, because we're going to add more memory pressure into the model, and the number of operations that we'll need to do at each backpropagation iteration will be exactly the same, but if we were to continue to accumulate the gradients onto the original matrices. So what can we do such that we have a matrix that has the same dimensions as the original model parameters, and that we reduce the memory usage and the number of operations? So something that we can do is take the delta W matrix and decompose it into a matrix multiplication of two smaller matrices. So here we have A and we have B, and we have B transpose A, which is almost equal to delta W. The trick is to make sure that the width of those matrices is small enough such that A and B are much smaller than delta W. So this kind of decomposition is not exact. So this is an approximation. We call that a low rank approximation. We are creating lower rank matrices and we are approximating the value of delta W by taking the multiplication of A and B. In practice, this is not too much of a concern because this acts as regularization. So we are learning the values of delta W by using the statistics of some training data. Usually when we fine-tune a model, we use much less training data that we use than when we pre-train the model. So in practice, it is not rare that we don't even have enough training data to get statistical convergence of the different values that we have in delta W when we fine-tune a model. So having less parameters to learn is actually a benefit that will help us to generalize better to unseen data. So how do we use this? So this is the original matrix that captures the learning that we do during the fine-tuning. And we can just replace those by two smaller matrices, A and B. We just have a matrix multiplication operation that happens between the two. So now we are approximating the delta of the gradient updates by the product of two matrices. And we can do that for all the matrices that exist into the model. So during the forward pass, we pass the input tensors through the original feed-forward network, and we pass them through the first A matrix. We take the result of this product and we pass it through the B matrix. At the end, we just add the resulting tensors to mimic this decomposition of terms. So remember that the original layers are frozen. We are not updating those anymore. So during the backward pass, we are only updating the B and A matrices. So we don't need to pass the gradients through the original matrices, we just pass them through the new B and A matrices. So during the forward pass, we need to pass the input tensors through the original matrix and the new added matrices. But during the backward pass, the number of operations is reduced quite a bit because we don't need to pass the gradients through the original matrices. So the backward pass happens much faster than when we pre-train the model. So the only model parameters that we need to update during the fine-tuning are those new added A and B matrices. So this will speed up the fine-tuning quite a bit. So let's look at an example to understand the difference that we have in the number of operations and the number of model parameters when we have the low-rank adapters versus when we actually computing the full matrix. So let's say that R is the dimension of this matrix, which is also the dimension of this input hidden state. And C here is the output dimension of this matrix. So as input dimension, I need R, and this resulting decomposition, we produce a vector of size C. Here I'm going to say that R is equal to 10,000, C is equal to 20,000, and R is equal to 4. So lowercase r here is the rank of those two A and B matrices. So let's imagine that we input this hidden state here through this delta W matrix. So the number of operations that we have to perform this matrix multiplication is 1, the dimension of the vector, R, which is the input dimension, and C, which is the output dimension. So we have 10,000 times 20,000, which is equal to 200 million operations. So the number of elements that we have in delta W is equal to 10,000 times 20,000, which is equal to 200 million elements in that matrix. Now let's consider the number of operations that we have for A times X, X being this input hidden state. So we have 1, which is the dimension of this vector here, times capital R, which is the input dimension to this A matrix, and lowercase r, which is the rank, which is the output dimension of this A matrix. So we have 10,000 times 4, which is 40,000. Now let's compute the number of operations that we have for B times the resulting matrix that is coming from A times X. So the matrix coming from the operations A times X has dimensions of 1 times R. So 1 is the dimension of the vector, and A mapped from capital R to lowercase r. So now the dimension of A times X is equal to 1 and R, lowercase r. The input dimensions to B is lowercase r, and the output dimensions to B is capital C. So the number of operations for this product is equal to 4 times 20,000. This is equal to 80,000. So the total number of operations to have X times A and then the resulting tensor times B is equal to 120,000 operations. And this is to be compared to the 200 million operations that we have when we have the full rank matrix. The number of elements is the same. We have 40,000 plus 80,000, which is 120,000 elements in the matrix A and B. So this means that passing this input tensor through A and B is much faster than passing this input tensor through the full rank matrix. And keeping in memory the matrices A and B is much easier on the memory than keeping the full rank matrix. So this low rank adaptation has huge advantages when it comes to speeding up the fine-tuning and reducing pressure on the memory.